Earth before the dinosaurs was not a quiet prologue. It was a brutal, alien world, where our distant relatives first learned how to survive in hellish conditions. You might think the time before the dinosaurs was just a warm-up act, a forgotten chapter before the main event. But if you stepped out of a time machine 299 million years ago, you wouldn't find a lush Jurassic Park. You'd find one giant landmass, Pangaea, baking under brutal seasons, surrounded by a global ocean and scarred by volcanism. The farther you walked from the coast, the hotter and drier it became, until the interior made the modern Sahara look forgiving. And the rulers of this world weren't dinosaurs. They were your distant relatives, ancient synapsids, the stem mammals that would one day lead to us. To understand why the Permian became such a nightmare, first visit the paradise it destroyed, the Carboniferous period, about 359 to 299 million years ago. Vast equatorial swamp forests locked away enormous amounts of carbon that would later become the coal seams powering our modern world. The air was different too. Oxygen levels were significantly higher than today's 21%, likely reaching roughly 30 to 35%, turning the atmosphere into a booster for animal size. On the forest floor, a millipede-like invertebrate called Arthropleura stretched more than 2 meters long, making it the largest land arthropod known from the fossil record. Above it, dragonfly relatives such as Meganeura flew with wingspans around 70 centimeters, roughly the size of a small bird. In this oxygen-rich air, flight for insects was easy, and gigantism came naturally. But this ecosystem had a hidden weakness. It depended on constant humidity. As the continents drifted together toward Pangaea, climate patterns shifted and the great swamps began to dry, fragmenting into isolated pockets of forest. Amphibians, dominant vertebrates of the time, were chained to water. Their delicate skin and jelly-like eggs desiccated in dry air. So as the wetlands vanished, many of them did too. In the background, evolution worked on a radical invention, the amniote egg. This egg carried its own watery environment, sealed inside a protective shell, allowing embryos to develop on land instead of in open water. Animals with these eggs, amniotes, could leave the collapsing swamps and push into the dry interior, where amphibians could not follow. These pioneers split into two great branches: Sauropsids, ancestors of reptiles and birds, and synapsids, the stem mammals that would eventually lead to you. By around 290 million years ago, Pangaea was fully assembled. The interior lay far from the stabilizing influence of the sea, so temperatures swung between scorching summers and cold winters, hammered by seasonal mega-monsoons. Among the amniotes, two lineages emerged. Sauropsids stayed relatively small and lizard-like, while synapsids, our side of the family, grew larger and took center stage as the dominant land vertebrates. The top predator of this red world was Dimetrodon. Often mistaken for a dinosaur, it actually lived about 40 million years before dinosaurs evolved and is more closely related to mammals than to modern reptiles. Its name means two measures of teeth, and its skull shows differentiated tooth types, cutting and tearing surfaces that foreshadow the complex teeth of mammals. The most iconic feature, its massive back sail, formed from elongated vertebrae covered in skin, likely helped regulate body temperature. Many paleontologists think this sail allowed Dimetrodon to warm up quickly in the morning by absorbing sunlight, reaching hunting temperature much sooner than its prey. In a climate with cold nights and hot days, that was a lethal advantage. Large amphibians remained cold and slow in the dawn chill, while Dimetrodon could prowl waterholes and riverbanks, striking before they fully woke up. For millions of years, sail-backed paleosaurs like Dimetrodon dominated the land. But as the Permian progressed, the world grew even hotter and more arid, pushing evolution toward a new kind of synapsid. By the Middle Permian, around 270 million years ago, Therapsids, more advanced synapsids, had replaced the old sailbacks. Their bodies and skulls began to look less reptilian and more like early versions of mammal relatives. One standout group was the dinocephalians, literally terrible heads. Animals like moschops were massive, barrel-bodied herbivores with thickened skull roofs that may have been used in head-to-head combat, similar to modern head-butting mammals in battles over territory or mates. These weren't agile fighters. They were biological battering rams, crashing together in slow, bone-shaking impacts in a world that was drying out and toughening. The real breakthrough, though, was in their posture. Earlier, synapsids sprawled with limbs out to the sides, forcing their bodies to swing left and right as they moved, which compresses the lungs and limits how long they can run. Therapsids began rotating their legs closer to the body's midline, adopting a more upright stance. That shift reduced side-to-side flexing and allowed them to move and breathe more efficiently at the same time, a key step toward higher endurance and, eventually, warm-blooded metabolisms. Then, the fossil record dims. A crisis called Olson's extinction hit during the Middle Permian, wiping out many large dinocephalians and other groups. The exact trigger remains debated, but big, heavy herbivores vanished, leaving ecological space for new predators to evolve. By about 260 million years ago, the late Permian world was under extreme environmental stress. Water was patchy, seasons were severe, and evolution responded by building heavily armored herbivores and specialized killers. The apex predators of this time were the Gorgonopsids, saber-toothed Therapsids, that ruled from roughly 270 to 252 million years ago. The largest, in Austransevia, was about the size of a large bear, but with a long body and an oversized skull. Austransevia carried elongated upper canine teeth, true saber teeth, up to around 10 to 12 centimeters long. To use them, it evolved a jaw joint that could open to an exceptionally wide angle, allowing those fangs to clear and slice deep into prey. Its main targets were parasaurs like Scutosaurus, bulky herbivores with thick, bony armor plates embedded in their skin. A normal bite wasn't enough. Only targeted, slashing blows to softer regions such as the neck could bring these tanks down. While saber-toothed Gorgonopsids ruled the open landscapes, smaller Therapsids called cynodonts lived in the margins. They were modest in size, often no bigger than a dog, but packed with features that would define mammals. Cynodont skulls show a secondary bony palate that separates the mouth from the nasal passage, letting them chew and breathe at the same time and supporting a more active metabolism than in many reptiles. Small pits on their snouts suggest whiskers, and by extension, some form of fur for insulation. Fur and higher metabolic rates point toward emerging warm-bloodedness, meaning these unassuming animals were refining the mammal blueprint in the shadows, even as the world around them edged toward disaster. Around 252 million years ago, in what is now Siberia, the crust of the Earth tore open. Instead of a single volcano, enormous fissures erupted sheets of lava in a flood basalt event now called the Siberian Traps. Over hundreds of thousands to about 1 million years, these eruptions poured out enough lava to cover millions of square kilometers in basalt, forming a thick volcanic plateau. The real catastrophe came when rising magma cooked through buried coal and other carbon-rich rocks, releasing vast amounts of carbon dioxide and other gases into the atmosphere. Estimates suggest thousands of gigatons of carbon entered the ocean atmosphere system, driving a runaway greenhouse effect. Initially, sunlight-reflecting aerosols and ash triggered a volcanic winter. Skies darkened, temperatures dropped, and acid rain battered already stressed ecosystems. As the short-lived aerosols settled out, long-lasting carbon dioxide and methane took over. Global temperatures rose sharply, and tropical seas may have reached lethal temperatures for many marine organisms. In the oceans, dissolved CO2 made the water more acidic, dissolving calcium carbonate shells and damaging the base of the marine food web. Warmer water held less oxygen, and circulation slowed, creating vast anoxic zones where typical marine life suffocated. In these oxygen-starved warm seas, specialized microbes likely flourished, producing toxic gases such as hydrogen sulfide that entered the atmosphere, further stressing life on land and potentially damaging the ozone layer. The result was the greatest mass extinction in Earth's history, the Permian-Triassic extinction, or Great Dying. Roughly 96% of marine species and about 70% of terrestrial vertebrate species disappeared. In the rocks, typical fossil pollen nearly vanishes and is replaced by a spike in fungal spores, evidence that global forests collapsed into vast fields of rot. The complex Permian ecosystems of sailbacks, boneheads, saber-tooths, and armored giants were dismantled in a slow, brutal catastrophe. When the dust settled, the survivors didn't look impressive. One of the most successful was Lystrosaurus, a stocky, tusked herbivore about the size of a dog. It was a burrower and a generalist feeder, exactly the kind of disaster taxon built to ride out chaos. In some early Triassic fossil layers, Lystrosaurus fossils make up the overwhelming majority of land vertebrate remains, suggesting it dominated ecosystems, left almost empty by the extinction. Alongside it, small cynodonts, the direct ancestors of mammals, hung on in burrows and nocturnal niches. The Great Dying ended synapsid dominance, but it didn't erase the mammalian line. It pushed our ancestors into the shadows, where they evolved fur, sharp senses, and warm-blooded endurance, while dinosaurs and their archosaur relatives rose to power. The Permian shows that evolution isn't a ladder of progress. It's a survival game in a chaotic universe. The giants of one era can vanish while small, adaptable burrowers inherit the future. Every mammal heartbeat today, including yours, carries the legacy of creatures that survived heat, poison, and near-total extinction. If you could visit just one Permian animal, would you choose the solar-sailed Dimetrodon, the saber-toothed Inostrancevia, or the unkillable Lystrosaurus?